All right, so today we're going to be looking at the 2006 M1 free response problems, and this one actually surrounds work and energy. So with the spring, so the problem goes: a long non-linear spring is compressed various distances x, and the force F required to compress it is measured for each distance. So, and there's a data table here that we have to fill in, and the equation they give us for the force applied by the spring is F of x equals a x squared, where a is a constant. So part A of this question first asks, what quantities should be graphed in order to yield a straight line whose slope could be used to calculate a numerical value for A, that constant? So the answer here, first of all, on the x-axis, based on the equation F equals ax squared, to yield a linear equation to calculate the slope, which would be A, we use the form y equals mx plus b, but here it doesn't look like we have a y-intercept. So the y here is the f, the m, the slope, is a, and the x-axis is x squared. So the y-axis is f, x-axis is x squared. This is in newtons, this is in meters squared. And the slope, or m, is a, our constant. So, and then for part B, it now asks us to calculate the quantities that are not given in the data table. So what we see right here is our data table, and they filled out data points for F and for X. And to find our x-axis, which is x squared, we simply square the values here, and we end up getting, if we're using two sig figs as seen here, we end up getting 0.0025, 0.01, 0.0225, but that rounds up to 0.023, 0.040, and then 0.0625, but rounding up to 0.063. So that's part B of our question. Yep. And then for part C, we're looking at this graph. So as we said before, the x-axis is x squared in meters squared, that's the units, and our y-axis is the force in newtons. And to use sort of the intervals that they've given us, we're going to use 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, and then here 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100 newtons. And now to plot the data points of x squared versus the force, so 0.25, that's like half of 0.05 at about 4 newtons. 0.01 at about 17 newtons, 0.0225, so like somewhere in the middle here, at around 38 newtons, which is around there. Then 0.04 right on this point at 68 newtons, which is close to here. And then 0.0625 or 0.063, so somewhere in the middle here, at 106, which is a little bit off the chart, so we're just going to plot it here. And then once we have this line ready, we're going to plot sort of a straight line. I'm going to use a straight edge here. It's not going to be perfect at all. Yeah, that's a little rough, but you get the idea. So, and as we said before, the slope of this linear equation right here is a, the constant. And part D, that's exactly what we're doing. We're calculating the slope to find a. So what we're going to find, so we did that, C is done. And then part D, what we're going to do is we're going to calculate the slope of this equation using the very basic idea that the slope equals the change in y over a change in x. And in this case, that's the change in our force over a change in the x squared. So let's just choose two random data points. Let's choose the last two data points. So 106 newtons minus the previous data point of 68 newtons over the corresponding x square values, which is 0.063 meters squared, since it's x squared, minus 0.040 meters squared. And that gives us a value of about 1,422. But if we're adhering to sig figs, we're going to use scientific notation, and that's about 1.4 times 10 to the third. And for units, since it's newtons over meter squared, newtons per meter squared. So that's part D, where we find the slope. And then we move into a second part of this question. I'm just going to move this over so you can see that. To a second part of this question, and that's where the spring is now placed horizontally on the floor, and one of the springs fixed to the wall. And now we have a mass for the cart. A cart of mass 0.5 kilograms moves on the floor with negligible friction and collides head-on with the free end of the spring, compressing it at a maximum distance of 0.1. And so part E asks us to calculate the work done by the cart in compressing the spring 0.1 meters from the equilibrium length. And we're going to treat equilibrium as 0 in this case. So to find the work done, we're going to use the basic concept that work equals Fx. And if you integrate that, that's work equals the integral of f dx, because we're looking at all the small intervals of x added up together. So to do so, we're going to use the equation that f equals ax squared that we've used throughout this problem. And so to integrate that, we know the limits are from 0 to 0.10 meters, since that's the maximum, that's the amplitude, that's the maximum distance from equilibrium that the spring can go. And we're going to plug in this equation for f in the integral, ax squared dx. And then we integrate that using basic integration rules, and we come up with 1/3 a x to the third from 0 to 0.1 are bounds. And once we use the final minus initial, plug those in, we end up with 1/3 times a times 0.10 to the third. And then we plug in the a we found in part D, the value of a, that constant, and we end up with 1/3 times 1.4 times 10 to the third newtons per meter squared times 0.001 meters cubed, since this is 0.10 meters and we're cubing that. And then the value that we eventually end up with is somewhere for work is somewhere around 0.47 newtons per meter, since if you use these units, they cancel out to be newtons per meter, or joules as we know them, the more common term or unit for work that we have. So now moving on to the last part of this question. Now it asks us to calculate the speed of the cart just before it strikes the spring. So now we're going to use another equation for work, which is essentially that work equals the change in kinetic energy of an object. And delta K for us equals kinetic energy final minus kinetic energy initial. So now we know that this cart starts from rest. So the initial kinetic energy is 0. So we're just left with Kf, which is, we know, is equal to 1/2 mv squared. So now we have this equation through all these steps that the work equals to 1/2 mv squared. And then if you want to isolate v, we move these to the other side. We get v squared equals 2w over m. And then take the square root of both sides. Root of 2w over m equals v. And now we have both w and m. Those are both known values for us. So v equals 2w over m. And then that equals 2 times 0.47 over 0.5, which is the mass that we got from the problem, 0.50, just to keep with sig figs. And that eventually equals somewhere around 1.4 meters per second. And that's just factoring into sig figs that we've kept consistent throughout the entire problem. And yeah, that's the end of this problem. And I think we've covered a lot of different equations and concepts of work and energy that are important to our lives.